So now let's start with a new topic called isomerism. Isomerism is a topic of organic chemistry, and let's get right into it. So first of all, what is an isomer? Isomer is composed of two words, iso and mer. Iso means similar and mer means structure. And the name itself should suggest that it means that they are compounds which have the same structure, or there is a little bit change in between those structures. Now, isomer is initially divided into two types. First, there is the structural isomers, and then there is the stereoisomers. Now, the stereoisomers are basically isomers in which there is a little bit difference in the geometry or how the atoms are arranged. Whereas in structural ones, there is a complete change in the structure itself of the atom. So the structure are divided into so many different parts. Okay. So now let's start with chain isomers. Now, as you know that a structure like this is a carbon chain, and the carbon chain is made up of many carbons, and this right here is having 5 carbons, and it is called as pentane. So what happens in chain isomer is that the carbon chain, with the main carbon chain, will be altered in one or the other way. So it can be altered like this. This can be removed and they can add it over here. This right here is 1-butane. As you can see, the structure will always remain the same. The molecular formula will remain the same. However, the name will change and the carbon parent chain will change. That's the only thing which you should remember of chain isomers. Next, moving on, we have the positional isomers. So, what is it positional? What is the difference between positional and chain isomers? Positional isomers cannot be applied to, can be applied only to a few things. Positional isomers can be applied only to functional groups. It can be applied only to substituents, and it can be applied only to multiple bonds. And it cannot be applied if anything over here is missing, right? And positional isomer just means that the position of carbon of these would change. And that's it for positional isomers. Next, we also move on to ring chain isomers. Now, ring chain isomers, you should remember the ring chain. As the name suggests, ring chain basically means that there is a ring and there is a chain. So, for example, if you take this right here, which is cyclopropane, the formula is C3H6. Each carbon has 2 hydrogen ions, and all of them must be 2 configuration. And as you can imagine, this is also the same type as alkene, and therefore it can also be written. The another isomer is like this. These both are also isomers because they have the same molecular formula, and therefore they are also called as ring chain, as one is a ring and the other forms a chain. Next, we have a few exceptional cases which you should be familiar with. They can ask a question like what is the minimum number of carbons required for positional isomer in alkane, and what is the minimum number of carbons required for using chain isomer in alkynes. So what happens is that you should be very familiar with structural geometry. So in this case, if you had some double bond or triple bond, it would be easier, as you can just interchange the double bond or triple bond. And actually, if you had any sort of structure present in here, you would be able to easily do it. However, there is no substituent and therefore we should make one. So this right here is minimum number of carbons required, which is 6. We require 6 carbons. And what will happen is that 2 of these carbon or one of the carbon will come like this. One will come here and the other one will go here. Now these both are the positional isomers in 6 carbons, and this is the answer. And what is the minimum number for chain isomers in alkynes? So what happens in alkynes is that, let's take 4 carbon alkyne. If you take this right here and if you attempt to join it over here, or if you attempt to do something like this and it will not be possible because the carbon over here will be attached to 5. It will be having 5 bonds, and that will not be possible. And therefore, what you should basically do is you can add one more carbon, and this carbon right here can be attached to here, like so. Now these both are isomers. Moving on with isomer, we reach functional isomers. Now functional isomers, the only thing you should remember is this big list of compounds that I have given you. So what happens in functional isomer is that the functional group will be different, or the formula will be the same. So for example, in alcohol and ether, one will be having something like this in the end of the chain, and ether would be in the middle of the chain like this. So what happens is when the OH molecule is brought from the end of the chain to the middle of the chain, the hydrogen molecule will join any one of these carbon, and it will be stabilized. Similarly is the case with aldehyde and ketone. There is a similar case with acids and ester. However, in isocyanide and cyanide, what happens is cyanide is like this, and this carbon will be attached to the main thing. And what happens in isocyanide is that the nitrogen will be attached to the carbon, and 2 bonds will be made to this carbon right here. And you know that nitrogen has one lone pair, bond pair electrons. It will be donated to this carbon right here. Similar is the case with nitro and nitrile. Attachment of N. And here what happens is the oxygen will be attached. Right. Then for primary, secondary, tertiary amine also is quite similar. This basically means the number of carbon that is attached to the nitrogen. 3 means will be having 3, 2 will be having 2, and primary will be having only 1. Next, let's continue to metabolism. So for metabolism, you should remember compounds that look like this over here, having more than one bond attached to it. They are the main part of metabolism. So what happens in metabolism is that if you take, for example, O, CH3, CH2, CH2, CH3, then you can think about these people playing a tug of war, and O is the middle part, right? So when they are playing tug of war, say for example this guy is really very strong, he would be able to pull all of them behind. So that's what happens in metabolism. The second isomer over here is CH3, CH2, O, CH2, CH3. So basically just take the carbon chain and push it like this or like this. However, one thing you should always remember is to read from here as well as here. So if for example you thought this right here would be a structure, then you would be wrong. These both are identical. How? If you just take the mirror image, then you can just superimpose and be the same thing. So that's all for metabolism, and next we have telomerism. Finally, we have the concept of tautomerism. Now, what does tautomerism mean? Tautomerism is basically, these are the 2 examples which I provide, and that's basically it. What you should remember for tautomerism. You can say that it is also similar to functional isomer. However,
The only difference is that here what happens is that there is one hydrogen in this, fine. So this one hydrogen will join to the oxygen. It will form a alcohol, and there will be a charge which will be made over here. A negative charge will be made here, and a positive charge will appear on this carbon, and they both will make a double bond. And that's the only thing you should remember. This is also another example of a tautomer, and only main thing you should remember is that stability of tautomer is greater than the I effect. And another thing you have to remember is about chain and ring tautomers. In ring tautomers, keto is greater than alcohol, and in chain it's the opposite. In this one, aldehyde is how I am saying aldehyde, alcohol or enol. Enol is more stable than this one. So continuing, we next move on to stereoisomers. Now stereoisomers, there are various types of stereoisomers, and now we will be starting with the configuration of stereoisomers. So what this configuration stereoisomer basically means is that there is a restricted system. In all of these cases, there is a restricted system, and and they can be easily rotated or placed in different planes, or they can easily be changed a little bit. And in the first case, we have double bond. So double bond, only thing you should remember is that there should be two carbon, and they should be having two different types of bonding here. And what is the main thing is that they should not be having same like AA in the same this thing. They should not be having in the same this thing. And the second thing is that it should all be different. So this right here is cis, and the trans version for this would be something like this is trans right here. And that's very easy to understand. Next we have the E and Z rule. So basically you can all scientists are all idiots, okay, fine, just remember that. So for E you can write it like this. The starting, if you remove this line which comes over here, if you remove that, then you see that you get the same format of a cis. If you had like a bond like this, it will look similar to cis. So you can remember it as cis. And Z, you could have remembered it as trans, right? Because it has like this, and the other one is going like this. It looks similar to trans. However, since these scientists are idiots, okay, the people who made this, they're all idiots. This right here would be trans, and this right here would be cis. Understood? Just interchange the positions and they will be proper. So cis is Z and trans is E. That's it for the double bond system. Next we have what is called a oxide. So oxides are basically nitrogen compounds. They have the structure right over here. C one and there's like H over here or OH over here, and this nitrogen can also be having OH. Okay, no, this OH you can put a CH3 here. And you know that there are a pair of bond pair electrons in the nitrogen, right? So these bond pair electrons will become the other end, like so. This is the structure of one of the oxides. What you have to assume is the OH and the H. Usually you don't represent this in the diagram. So if the OH and H are in the same place, you have cis. And if they are indifferent, if they are so, then you have a trans. That's it. Similar. But the thing is, they don't have the names as cis and trans. Only the double bond systems will be having cis and trans. What they have over here is syn and anti. this right here would be anti. Anti, you can remember it easily because they are in opposite sides. Sin, you can remember it because it's in the same side. Now next, let's move on to NH2, NH2. Next we have this solar system. This solar system is having a double bond, and there is again a lone pair over here, and there is a lone pair over here. And usually there is a phenol or a CH3 over here. That does not matter. The only thing that matters is the lone pair of electrons. So lone pair of electrons in the opposite direction, trans. So however there is no trans in nitrogen compounds, so you can call it as anti. They are in the same direction, then it will be called as syn. Right? Now after this we have the main part, and the main thing about the next one is the concept of stereo center. So if a compound exhibits a stereo center, it basically means that there is a restricted system in there. So if there is a restricted system, then you can say that you can say easily that there are configurational isomers can easily be formed. So for stereo centers, one of those things is this would form a stereo center, and this would also form a stereo center. And the thing we should move on to next is the cyclic compounds. So cyclic compounds, for example, if you take cyclopropane, correct? And if you attach like two substituents, there is one always key rule. There should be two substituents. Right? So there should always be two substituents, and those two substituents can be attached to any end of the same. So you can be having CH3 here and CH3 here also. Here it will be H, here it will be H. You can say that if you place them on a plane, then these all form tetrahedral structures. So these, if you take two tetrahedral structures and if you place them like this, you can see that one will pop off like this, the other one will pop off like this, and that is basically what we are looking at. If you look at them from a horizontal level, and if you like take this as a plane, so this will be on a plane and this will be up and down. So this right here would be cis, and another structure like this. Having a CH3 top, and this would be trans. Therefore, all cyclic rings which have two substituents act as a configurational isomer. Fine. So next we move on to the final type of isomer, and this final type of isomer exists only with compounds with greater than 6 carbon ring. And the second thing you should be having is a double bond in ring. Right? So for example, if you take octahedral, fine. So this right here is a structure of octahedral. Usually if you just attach a chain to it, it usually does not form an isomer. If you have, however you can form one of these types of isomers. If you have two substituents, then you can form an isomer. However, what the theory says is that if there is a double bond right over here, then these two can act as a stereo center. Right? So these two will act as a stereo center. This usually forms a 3D geometry figure, and because it forms a 3D geometry figure, it can exhibit these things. It is not possible in structures like hexane. If you do like this, then this is a revolution. Right. Okay, so continuing with covalence. Covalence is basically structures which have this type of carbon in them. So if there are like two or more than two double bonds without like a single bond in between two carbons. Okay. So these types of structures are given the name of covalence. And covalence, you can be having even number or odd number of double bonds. If you have like odd number of double bonds, it will look something like this. Right? But one thing you should remember is that these double bonds cannot be considered as stereoisomers double bond. So they are not this. and these do not show stereoisomers. However, these right here, all these three can be made into one double bond, and it will act as one double bond, and therefore it will be having one stereo center. And you should just remember that. And that's all for chemins. Next we move on to the formula. Finally, we have a formula for finding out the number of geometrical isomers in a compound. So if you have like a double bond system like this, then what does dissimilar end and what does a similar end mean? So dissimilar end basically means that in the first double bond, the group which is over here, let's call that R1, and in the last double bond, the group which is R2 over here. Now these two are not similar, and that is what dissimilar ends mean, and the formula is very simple. It's just 2 to the power of n in case of dissimilar ends. However, what if R1 and R2 are equal? Then you get dissimilar ends. And here there is two cases. You have one n equal to even and the other n equal to odd. And in this, one thing is common. 2 to the power of n minus 1 is common. It will always be exhibiting 2 to the power of n minus 1 isomers always. However, in case of even number of n, and n basically is the number of double bond. Okay. So in even number of double bonds, the formula is equal to 2 to the power of n minus 2 by 2. In odd number, it is equal to 2 to the power of n minus 1 by 2. So the total number of geometric isomer in a similar molecule is 2 to the power of n minus 1 plus 2 to the power of n minus 2 by 2. And in odd, it will be 2 to the power of n minus 1 plus 2 to the power of n minus 1 by 2. And that's all you have for the number of geometrical isomers. Next we will continue with the optical isomer.
Okay, so now let's start with optical isomerism. So what does optical isomerism means? So what the scientists discovered is that when they are sending some plain polarized light through some liquid having some organic solution, they see that the light would bend. Okay, it would bend either to the left or it would bend either to the right. And they gave a name for these. So if it bends left, they called it levo rotatory solution, and if it bends to the right, they called it dextro rotatory solution. But the question started to question why they are bending. So after this invention, what happened was it led to the formation of four bonds which you can make. Now what happens in a chiral carbon is that all the four bonds are all different. This will be some A and this can be some B. This is NH4, NH2, and yeah, it will be different for everything over there. This will be D. So if it's having everything different, then you can say that this is a chiral carbon. And chiral carbon can be represented in one of two ways. And the first way is via dash and wedge. Now, what do you mean by dash and wedge? So dash and wedge, and you can say that this is sp3 figure, right? So dash and wedge is the easiest way how you can show the 3D figure. So when the dash means the element which is closer to you. So in this case, I take it as n. In this example right here, it will be the element D. Dash is the thing which is closest to you. Next you have the wedge is the thing which is closest to you. The dash is the thing which is farthest from you. So it will be B in this case. Then you can exhibit the upper tube, A and H2 in this way.
So this right here is the dash and wedge sort of way of denoting a chiral carbon, and the thing about this is that you can easily just say the rotation using in this thing, whereas the other thing is the fissure, and this right here is the fissure. So next, let's continue with the rotation, which is given as R and S. An easy way to remember how the rotation occurs is that in case of clockwise, okay, it will come like this. You can imagine the R having this arrow like this and like this. So if you get some clockwise direction spin, then it is an R. And next we have an S spin, which is like this. So S, you can think of it like this. You see? Or if you are better using cursor handwriting, you do like this. So you start with this, and again. This is an easy way to remember the R and S for wedge and dash. So in wedge and dash, what you should basically do is, you know the CIR, which says you to go from the highest atomic number. Similar concept will be used here. So I have a compound over here. This is a 3D and sp3 configuration tetrahedral. So it's like 2 will come like this and 2 will be in front, and this right here is in front and this is behind, right? So how do you find the rotation for wedge and dash compounds? For wedge and dash compounds, it's really easy. First you number them. This would be first, then you will get this, then you will get this. And this hydrogen right here is not required, the last compound, so it's having the least atomic number. And the rotation is really simple, it's just 1, 2, 3. Now R, you can see that this is going to be, so it forms an R. So this is an R. Right? That's all that is to in this concept, and that's all you should remember. Another thing you have over here is chlorine is the highest, so it will be number 1. Here you have oxygen and here you have a nitrogen. You can say is CNOF. Oxygen is after nitrogen. So oxygen will be given the priority as number 2. Nitrogen will be given number 3, and this would not be worried about. So you have like this, and this will be S. For wedge and dash, that's all you should remember. Another thing you should be knowing when this concept comes up is how you can transform a wedge and dash into a fissure product. So if you want to convert them from a wedge and dash to fissure, you should always keep them in this format. It should always be having a wedge in the bottom right, and it should always be having a dash in the bottom, in like the top right. And how do you do that? You should be having the ability to imagine the compound. So I will come to that later. So how do you write this first of all? This you basically take the wedge and put it to the left. Fine. Then then the dash would be basically behind that. Fine. So it will be CH3. Then you can just copy down the top and bottom as you can see. C over H, and this will be H. And that's all for this, for converting this to the fissure. However, for this you can see that the compound chlorine is having on the wedge, however it's to the left, the wedge is to the left. You need to get this chlorine over here. And how do you do that? And you basically do that by taking the compound and by rotating it. So the chlorine is in the wedge, it's in the bottom right. You should rotate this in such a way that this will go to the back and it will be having the dash. So this will be converted first into C. And the dash will be chlorine as you rotate it like this. Take like this and you rotate like this. And here would be BCl. Right? And again you can write the figure. It will be Cn. That's it. There is one thing you should be knowing about the wedge and dash projection. So when you are finding the rotation for the wedge and dash, if the hydrogen is present in the wedge over here, then you should always change this spin. So here you can say this will be number 1, 2, 3. It will be like this. So it will be a R. Correct? So it will become a S, and S will be the answer. That's it for the wedge and dash projection. The Fischer projection is a projection in which the carbon will be present in this type of structure. The carbon will be present in the center, and the 4 bonds will be indicated by the lines. And the lines indicate the lines are basically this thing, and one thing you should be knowing when finding out the spin in this Fischer projection is that you follow the normal rule. This will be number 1, this will be number 2, and this will be number 3, and you go like this. So this right here would be S, correct? So since this is S right here, the only rule you should remember is that the presence of the hydrogen is the main thing which would affect the spin. If the hydrogen is, for example, present over here, and the OH is in the vertical line, then you should always change the spin. So if it's in the horizontal line, then this would become R. You can see the direction is always correct. This will be number 1 itself, 2, 3. Since the hydrogen is in this horizontal line, it will change. So S will become to R and R will become S, respectively. That's it for Fischer this thing. I'll take another example. This example right here is cut this out. Okay, straight from here, pick. So one advantage of the Fischer projection is that you can find the spin of rather complex diagrams. So for this right here, as an example, you see that all of these are having different things. Now these are the carbons which are in the middle, and you can see that this carbon and this carbon are connected. So what does that mean? Is this even showing optical isomers? Yes, it is showing optical isomer because this is different, this is different, this is different, and this entire thing over here is attached to this carbon. So this entire thing is one thing and it's different from everything else. So yes, chirality, chiral carbon, both are present. Correct? Fine. So how do you find the spin of this right here? So this will be number 1, this here will be 2, and this entire thing for this compound, the above chiral carbon, would be number 3. So the spin again would be like this. However, since CH3 is in the horizontal, the number 4, if the fourth this thing is in the horizontal, then you should always change. So this usually was S, would become R now. Correct? S would become R. So similarly for this one also, it is also this would be what? This would be R, and R, since CH3 is in the other thing, will become S. Next we have the concept of shift and mirror. So we have some direct compounds over here, and basically what I have done in the first case is that I have shifted the NH3 and H. So we can say what happens to the spin when you do something like this. So always when you change one thing, the spin always changes, right? So here the spin, the direction is like this. Yeah. So it will be a S. However, hydrogen is present in the horizontal, therefore it will become R. In this also the spin is the same, but the hydrogen is present in the vertical, so it will be an S. That's the only difference. Here you can observe that the spin is going like this, so, and the hydrogen is there. So this also is basically the same compound here. This you can see that it's going like this, and the hydrogen is there, so it will become S. So mirror also will be having the same thing. These two carbons will change. If the mirror is over here, these both will change. The concept is still the same. The spin will just change. We have some concepts which are related to the spin. So what are there are enantiomers, diastereomers, identical compounds, and mesomers. So first of all, let's start with enantiomers. So what are enantiomers? Enantiomers are basically compounds which are mirror images of each other. However, one condition should be met, that is, they should not be superimposable. If you take this and put it over this, you see the OH will come in this and the CH3 will come over this. So that's the only concept of enantiomers. If they are like two compound system like this, then if for example they are R and S, so the enantiomer of R and S would be S and R, which is basically the mirror images. As if you put a mirror, R will become S and S will become R. So similarly we have diastereomers. So diastereomers are basically similar compounds, however they are neither mirror image, they are not mirror images. So they can be something like this, H, OH and CH3. This is a diastereomer. Now if you see that if you just do a spin, then you can say that the spin basically changed, right? Yeah. So if you take another example of R and S, the diastereomer of this will be R and R. It can also be S and S. Okay. Next we move on to identical. So identical basically means that the compounds are basically the same, right? So when are the compounds same? The compounds would be the same if they have the same spin, right? So this right here is an R spin and this will be having an S spin. If you pause the video and try to find the spin of this one, you will find that this is also an R spin and this right here is an S spin. So basically these both will be identical. So if there is an R and there is an S, then this should also be R and an S. And sometimes what happens is they can also take the compound like this and they can just spin it out, right? When they do such, then you will get the answer as S and R, correct? Because they just spinned it. So what? Yeah, basically if there is a compound like COH over here and the compound here is not COH, try to make it COH, and then if you compare, then you will see that it's also R and S itself. Now finally we have mesomers. What are mesomers? Mesomers are basically chiral compounds, chiral carbon compounds. However, they do not exhibit chirality. This right here is a chiral compound, this is also a chiral compound. You can, however, draw a line like this, and all of a sudden you have a plane of symmetry. So since there is a plane of symmetry, it does not optically active. Now these are some special isomer names you should be remembering. So continuing with the topic of optical isomerism, in order to find the number of isomers, optical isomers present, you have this entire table you have to memorize. Symmetric is to the power of n, symmetric and even is to the power of n minus 1 and plus 2 to the power of n minus 2 by 2. You just add these both and you get this thing. Again add this and you get this. Then another major concept you get is the D and L shift. For D and L shift, what you should remember is that you need to check the last chiral carbon. Correct? It's usually last but one carbon. Okay. So if you see the last chiral carbon, it will be having OH and it will be having H. So if the OH is on the right side, then it's D or dextro, and if the OH is over here and this right here is a H, then it's L or levo rotatory. Then you have the concept of specific optical rotation. Okay, so specific optical rotation basically says that the alpha or the degree of this specific optical rotation is equal to theta, which is the degree by which the light has been changed. So if this is initial, then this would be theta, correct? Then theta divided by the length of the polarimeter times the concentration, which is basically moles, correct? Moles of the liquid. Now, use this formula and you get specific optical rotation. So finally we have the topic of conformations. So conformations, actually you have to memorize only these four things right here. So conformations basically are those form like structures which are the most stable in these compounds, right? So they can be expressed in two ways. One is this is called a sawhorse, and if you basically just take this and if you see from this side here, if you see from here, then it looks something like this, okay? This right here is the front carbon and the bigger circle is the behind carbon. And for stability, you should just memorize this. For this right here, you get gauche, which is basically 60 degrees. Okay. This here is anti, 180 degrees. This for this compound, what you have to remember is that the diol, the hydrogen and the oxygen will be attracted, and this causes hydrogen bonding, and this makes this compound stable. Okay, so the conformation for this compound is also gauche, and the conformation for this compound right here is also gauche, because hydrogen and fluorine will make a bond. So basically you should just remember the names and whatever it is. It's quite easy, and these are the conformation name and this is the structure.